All right, let's do some free response for Physics 1. The multiple choice portion was definitely quite difficult, especially if you did it in the time constraints. So I tried to make a pretty moderate FRQ set. I think we'll find that most of them are pretty standard, but there's a difficult part or two in some of them. So I usually think that question 1, which is the mathematical routines, has the potential of being the hardest because it's just derivation based. So we're going to start, and our instant thought when we see any sort of a ramp is that energy is probably involved. So this is a pretty well known scenario. We have a block that's released from rest. The block slides down a ramp and travels through a circular loop whose diameter is given. All surfaces are frictionless. So this is just our classic place an object on the ramp and have it loop the loop. So I tried to keep a pretty straightforward scenario here. Now for the MR, you can be given a representation before or after deriving an expression. Here, we obviously are doing it first. So we want to draw and label the forces, not components, acting on the block at each of the following locations. So we have location X, which is when the block is at the bottom of the loop. And then we have Y, which is when it's traveling up the loop. And it's at the sort of 3 o'clock position. So there's no grid here, which means we just got to get the forces right. We don't have to compare them or anything. So what are the forces? Well, absolutely, we know that at both positions, we're going to have a gravitational force directed downward. And then at position X and position Y, well, the only other thing touching this object is the loop or the surface itself. So the only other force we're going to get is a normal force. And the normal force is the force exerted by a surface, so that is always perpendicular. So we have a normal force directed upwards at position X, and we have a normal force actually directed to the left at position Y. So, because again, it points perpendicular to the surface. So here, that sort of difference, that normal force is helping supply the centripetal acceleration as this block moves around the loop. So we know there has to be some sort of force pointing towards the center. So a common trap would be calling this like centripetal. Centripetal force is not a noun. Centripetal is an adjective. So if something goes in a circle, the force causing you to go in a circle can be described as centripetal. It's not a noun, so it shouldn't be on these force diagrams. Now you could call FG, MG, or any reasonable label works. So how do you get your points? Well, A1, you got to get your FG at both locations, and for A2, you have to get your normal force at both locations. So pretty easy to get A1. A2, you have to notice the perpendicular effect. Drive an expression for the minimum speed v top required such that the block remains in circular motion at the top of the loop. Express your answer in terms of r and physical constants as appropriate. So what is the minimum speed at the top that we need to continue going in circular motion? So first of all, we have to think about why that's even a value that exists. So there actually has to be a speed that exists, because if I have just the right speed, that I can make it from the bottom of the loop to the top and stop via energy conservation. Well, if I'm stopped at the top of the loop, I'm stopped. So that means I'm going to fall right down. So I must have some sort of velocity component going to the right, or sorry, to the left at this time. So that's why we have to have that. So what is the condition here? Well, the condition is that we are in circular motion. So the fact, I was very particular about including that word to really tell you that this is centripetal related. So what we need is that we are in circular motion. So what that tells us is that the net force is supplying a centripetal force. So what are our forces on the top of the loop? Well, if I place my block at the top of the loop, gravity is pulling me down, and the normal force is pushing me down. So F net would be equal to Fg plus F normal. But if we find the minimum speed we can go and still get over, means we're just barely losing contact. So we actually take out this normal force term, because if you find the minimum speed, that's right when you start to lose contact. And if you lose contact, the surface isn't touching you anymore. So we can just set our net force equal to mg, and F net is ma. So ma equals mg. So we get that our acceleration is equal to g. So it sort of looks like a free fall situation, but we actually want the speed. So then we just have to use our relationship. We have to use our relationship that we know for traveling in a circle. Acceleration is v squared over r. Just blocking this out here. So we can say that v squared over r is equal to g. So v squared is equal to gr. So v is equal to square root of gr. So the MR is worth 5 points, and I split it into a 3 plus 2 here. So to get A3, you have to have some sort of multi-step derivation involving centripetal force or centripetal acceleration. You get another point, A4, for indicating the acceleration is g. And you get point A5 for the correct answer. Then, now that we know what the speed has to be at the top, we can now figure out the height we need to go through the loop, or completely thorough the loop. It's spelled right, so it didn't get flagged, but obviously this should be through, not thorough. That's what I get for writing this today. Okay, so we want height. We just found speed. So anytime you have height and speed changes, it's totally energy. And also, quick tip. We are only going to give you letters in the derived questions that appear in the answer. So the only letter that's not a constant should be r. And notice it is. Same idea here. Our height should also be in terms of r only. So now we can just do a quick energy conservation. So I think it's probably easiest just to kind of do the bar chart equation. So I call this the bar chart equation when you sort of equate the energy bars. So we're at on top of the ramp, then we're at top of loop. So when we're on top of the ramp, all of our energy is in the gravitational potential energy bucket. And then when we're at the top of the loop, we still have some energy in the gravitational bucket because we're still above the ground. But we're also giving some energy in the kinetic bucket because our block is moving. So if we were to set up an equation that explains what's happening, since we know the total energy is going to remain constant, we can just say that the initial gravitational potential energy gets turned into the sum of kinetic and gravitational potential at the end. So initially, we know that U is mgh. So mgh is equal to 1/2 mv top squared, because kinetic is 1/2 mv squared. And we use mgh, but at the top of the loop. So here's actually why I gave you the diameter of the loop instead of the radius, because I wanted you to be able to see that this is a height of 2r. So I thought that would be easier for you to identify the height as 2r. Okay, and then we solve. Maybe I should be consistent with my letter M. Okay. Now we do some simplifying. So the m cancels. Well, let's plug in some things first. So we'd get GH equals 1/2 V top squared plus 2GR. Then we can plug in, because in our previous part, we derived that V top is equal to the square root of GR. So V top squared would be GR. So I get GH equals 1/2 times square root of GH squared, or square root of GR quantity squared, plus 2GR. Notice that we now would get GH equals 1/2 GR plus 2GR. Everybody brought G, so G cancels. So we get H is equal to 1/2 R plus 2R. So what is 1/2 plus 2? Well, 2 is 4 halves, plus 1/2 is 5 halves R. And nice, that only has R in it. No other variables. So how did you get your points here? Well, we get 1 point regardless of what's happening for a valid statement of conservation of energy. So that would be A6, a valid statement of conservation of energy. It could be an equation form where you're plugging stuff in, or it could be something that looks like this. So it has to be a valid statement. You can't just say energy is conserved. You have to explain that there's sort of this conversion happening in some way. Then to get A7, you have to get a correct answer, consistent answer based on your V top. So it has to be correct based on what V top was. So that means if you don't get the correct loop height of 2R, you can't get A7. So A7 is really awarded for picking out the height as 2R and substituting in your V from the previous part and getting a correct algebraic final answer. So this is one we're grading on consistency, not correctness. And we go back and forth because whatever double penalizes you the least is the one we'll choose. All right, and then the part B of the MR for AP1 and AP2 is actually a claim. So it's a sort of like, we change the scenario, or we give you a new scenario, and you got to make a claim. So in this scenario, we replace the block with a sphere, and now there is friction, which allows the block to roll without slipping. The new height required for the sphere to move completely through the loop in circular motion is h nu. Okay, we got double thorough. We get the idea, though. So we're basically saying if instead of a block, we replace it with a rolling sphere, do we have to drop the sphere from higher or lower to get it to loop the loop? So so again, we could try to construct sort of what the main difference is and get the answer after. So what is the purpose of using a sphere or any rolling object? Well, it's rolling. So the key here is that since it's rolling, the rotating sphere has both rotational and translational kinetic energy. Because if it's rolling without slipping, it is translating and it's rotating. So think about your justifications not as like you're trying to convince us. Think of your justifications as what physics facts are the most helpful and relevant. So usually one of these is like a fact about the scenario, and one of these might be like a specific physics principle. So here we have the rotating sphere has both rotational. Can we salvage this? No. Rotational and translational kinetic energy. So why does that matter? Well, that means that if we think about our bar chart approach, yes, it's true that like if we start from the same height, assuming our like mass is the same, although it doesn't end up mattering, if we pick the same sort of initial conditions, we still have UG. And we also are going to fix kind of where UG has to end at. If we have a rotating sphere, there's these two kinetic energy terms. There's the translational KE, and there's the rotational KE. So the rotational kinetic energy is sort of, it's not helping you go around the loop at all, right? Because you have to be translating to get that centripetal acceleration that we need. So this extra rotational KE is sort of siphoning off some of the velocity from the center of mass, right? Because our velocity is going to decrease compared to what it was before, because you have to split that energy between rotation and translation. So all of that, just to say, that's a lot of words I just said, and we're just going to boil this down as since KE splits between rotational and translational, we get a lower V for the same height. Right? So if I drop the sphere from the same height that I drop the block, the sphere is going to have a lower center of mass velocity or translational velocity, because I had to account for the fact that some of that kinetic energy has to go to the rotation. So all that is to say that h nu has to be larger than the original because of this fact. So to get B1, you had to pick this. To get B2, all you had to do is identify that there's two forms of rotational kinetic energy. And then B3 is some variant of stating that the kinetic energy is being divided, which is going to decrease your speed or anything equivalent to that. Now, if you want to like run an explanation by me, you can comment that, but it's anything in the spirit of this. So these explanation points are usually pretty flexible, unless if it's like a just straight up fact. Like this one is not flexible. Like I can't really think of a way you'd earn B2 without saying something like that. But there's a million ways you could say B3. We haven't even talked about friction or acceleration. There's some interesting ways of doing this. So don't think this is the only way. So I would definitely say that this is, in general, the MR can be the hardest problem because there's just deriving. Now, in my specific test, I actually think the hardest problem is my TBR, probably because it's fluids related, but there's a couple interesting things there. So I promise questions 3 and 4 are actually quite routine. I just wanted to give a nice fluids example. And I also looked at kind of what areas were over and underrepresented on the multiple choice, and there wasn't a lot of Bernoulli. So I needed some of that here with the TBR. Water with density rho is moving through the curved pipe shown in figure 1. Assume steady incompressible flow, of course. At position X, the pipe has area A, and the water speed is Vx. Position Y is a vertical distance h above X. At Y, the pipe area has 2A. So this is A, this is 2A. And we see that Y is elevated relative to X. So that's how you know this is a Bernoulli problem, because you have these different things happening, right? The pipe is widening, the pipe is getting taller. So there's these sort of energy-related effects. So the TBR, it's really like solving 3 problems in parallel with one another, where we give you a representation, a derivation, and a graph. Theoretically, they can be done in any order. So I usually think it's a good idea to read the whole TBR first. That's kind of a good idea for any question, but it's especially good for the TBR. So I am almost confident any form you have will have some sort of a bar chart to draw. Now, I chose a bar chart that's kind of interesting here. This is not an energy bar chart. This is what we call a Bernoulli bar chart, because it's not quite energy. It's really these like pressure terms. So I give you sort of the filled out quantities at position X, and I partially fill it out for you at Y. And we're just asked to create a possible bar chart. Then we have to derive an expression of the pressure differential between X and Y. So what's the difference in pressure between those? Then we have to sketch a graph of the speed of the water at y as a function of the area A of the pipe. And we have to label its maximum value. Assuming the height change is the same. And then suppose the area of the pipe at position y is increased to 3a. So the D part should be last. The D part is usually like we change something. So think about A, B, and C, and then we can deal with that. All right, so we'll just go in order. So we know this is going to be related to the Bernoulli equation because these are the Bernoulli terms. So Bernoulli says the sum of pressure plus 1/2 times density times speed squared plus rho GH is a constant. So that's why we like bar charts, because we can show sort of how these quantities are splitting with one another. So what that allows us to do is we just need to figure out how one of these things changes because we make the system the same. So if we look sort of at our bars here, our pressure, we have 3 bars. Our sort of kinetic term, we have 4 bars. And our gravitational term, we have 0. So that would be a sum of 7 bars total. And now we have to figure out how to actually split this. So I gave you the pressure. I gave you the pressure term. So I'm telling you the pressure actually decreases. So now we got to figure out how the other things change. Now, you can actually do this quantitatively, but we're actually not grading for that on this specific chart. So let's try to figure out what happens to the kinetic related pressure term. So the only thing that can change is V. So we have to think about what's going to happen to V. So notice here, the water is flowing from a small area to a large area. So anytime you have a size change, it uses the continuity equation, because we know that the flow rate, which is equal to the volume of water per time, must be a constant. That's what it means to be incompressible, right? The amount of water that flows through this section of the pipe must eventually enter the next section of the pipe, and so on. So if you have a larger pipe area, then your speed doesn't need to be as large. So this is also written as A1V1 equals A2V2. So we can see that since the area got larger, the speed must compensate by getting smaller to make the product the same. Now, we can also do this quantitatively because we know that we actually know the factor. So if we look at A1V1 equals A2V2, we actually were given that the area at y is twice the area at x. So we can say that this area got multiplied by 2, and this speed must have therefore have been halved to compensate. So all that is to just get us to figure out that the speed has to go down. So if the speed goes down, the kinetic Bernoulli bar goes down. By how much? We actually don't care. I chose to not care about that in the scoring guideline because I thought this question was tricky enough. But if you notice the speed halved, kinetic energy is 1/2 mv squared. So actually that means your energy gets quartered. So that's 1 bar associated with kinetic. And then you just got to make it all sum up. So rho GH, well, I have 7 bars total, and I have 2 bars right now. So rho GH must be worth 1, 2, 3, 4, 5. I don't like this, actually. I don't like my little shading in this. I'm just going to keep this at 5. So how do you get your 3 points here in the TBR? Well, your first point, A1, is for the rho GH bar increasing. Because if you're going up in height, I think that's the clearest one to actually get, is you know that the height bar has to go up. By how much? We don't care. To get point A2, the kinetic Bernoulli bar has to go down. And to get A3, you need 7 bars total. That's your conservation part. So notice we can get all these points independently. So you could have drawn any sort of values for rho GH and 1/2 rho V squared as long as it follows this criteria. So you didn't have to quantitatively get the fact that the halving of the speed occurred here, which quartered the KE term. Not important. But that will help us here when we have to find the absolute value of the potential difference. I'm so used to E&M of the pressure difference between X and Y. So anytime you're doing 2 locations, it's Bernoulli. So we have pressure at X plus 1/2 rho V squared at X plus 1/2 rho GH at X is equal to, not 1/2, sorry, oops, plus rho GH is a constant. So we just copy everything over, except we do it for Y. So now it's time to start plugging in some things, because there's a lot of terms here. So what we know first is that we can always set the lowest point of the Bernoulli equation to be our 0 height. So since our water is climbing up the pipe, we can just say that the height term is 0 here and replace HY with capital H. So now that gets us to pressure at X plus 1/2 rho Vx squared is equal to pressure at Y plus 1/2 rho Vy squared plus rho G capital H was given. And what we actually want is the pressure difference between the 2 points. So we can start moving things around, but notice we don't have the speed at Y, which would be helpful for us to have. So that's part of this derivation, is we got to figure out the speed at Y. So that uses continuity. So when we saw that there's these two, when we saw there's this equation that AX Vx equals AY Vy for continuity, we see the area at X is A, the speed at X is Vx, the area at Y is 2A, the speed at Y is Vy. So we see that a bunch of stuff cancels, the A cancels, so we get Vx equals 2Vy, or Vy equals 1/2 of Vx, which is what we expected earlier, that we knew the speed should have. So now we can substitute that in there. So we get Px plus 1/2 rho Vx squared is equal to P at Y plus 1/2 rho 1/2 Vx all squared plus rho GH. So we get Px plus 1/2 rho Vx squared equals rho Y plus, squaring this gets a quarter. So half of a quarter is an eighth, so plus 1/8 rho Vx squared plus rho GH. And we just solve for our pressure difference term. Now there's other ways of doing this where we could have actually set this point to 0 pressure and called this term delta P. That actually works too. But I'm just showing the more traditional way. So now I can just solve by moving some stuff around. So I could get Px is equal to Py, and then I get an eighth minus a half, so 1/8 minus 4/8, which would be minus 3/8, plus rho GH. And then I get my pressure difference. Px minus Py is equal to rho GH minus 3/8 rho Vx squared. Ugly, ugly, ugly. So this I included to have a challenging fluids question, by the way. This is way harder than anything you'd expect, probably. Fluids are Bernoulli related. There's a lot of computing going on here. But that is our answer. Now, you could have any variant of this. There's like a million signs, right? It just has to be these being subtracted somehow. The order doesn't matter because we want the absolute value of this. So how do you get your points? You'll notice this is a really hard problem, but it's actually really easy to earn some of the points. You get 1 point for using Bernoulli. That's B1. You get a second point for attempting to use continuity. You get a third point for correctly relating the speeds. And you get a fourth point for the correct answer. So all of this garbage algebra, the squaring and the moving, all of that was just for B4. So if you had a general idea that this was a continuity Bernoulli equation, you could totally get 2 or 3 of the 4 points without having to crunch a lot of the algebra. So that's why just kind of knowing roughly what to do is kind of the objective. The more specific niches of the problem, that's really to get your sort of final points. Those are your big 4 or 5 differentiators. But general competence gets you most of these. So again, we just did the Bernoulli equation. So multi-step with Bernoulli gets B1. Continuity setup gets B2. Correct continuity solution gets B3. And all that substituting back in gets you B4. All right, on figure 3, sketch a graph of the speed V of the water at Y as a function of the area AY of the pipe at that position, assuming it is always going to be greater than or equal to the area of the pipe at X. Well, here we're just using this fact that A1, or we'll call it X, AX VX equals AY VY. So remember, if your pipe is bigger, your fluid doesn't have to flow as quickly to get the same volume through it. So we can think of like the extreme case, where if I have a super, super, super big pipe, well, even if the water is just moving really slow, you're getting that volume through. So we know it should be some sort of decreasing curve. And then we also know that if your area is the same, based on this equation, if my area of y is equal to my area at x, well, that must mean my velocity at y is equal to my velocity at x. So we also know that at a, this value is actually vx. So we get this curve. Why do we get this curve? Well, we know that if the area of the pipe is the same, so this is sort of this idea where the pipe is about the same radius. So this is same radius, same area of pipe. And this would be a larger area. And we know it decreases non-linearly because if you graph this, you'd get like a reciprocal function. And it can't be linear because that would mean there's a spot where it just hits 0. And we know that doesn't happen. So this is actually quite tricky to get your 3 points here. So this is what I thought the hardest part of the TBR was. So to get C1, all you need is a decreasing curve. For C2, you needed a nonlinear curve. And for C3, you needed V at A is equal to Vx. So that's how you got your 3 points. You needed a decreasing nonlinear curve with a value of Vx when the area is A. So that's kind of a tricky graph for sure. All right, suppose the area of pipe X is increased to 3A from 2A and remains at a height h. Describe how this will affect 2 of the bars drawn in part A. Justify using your graph from part C. So what is the most direct change from this? Well, we know that area is going up. So if it's area, we're going to use continuity yet again. So we know it's AX VX equals AY VY. So we know that this term is constant, right? AY VY must be a constant. So if you are increasing the area, you must decrease VY. So the most direct change of this is that, and we can see that from our graph, right? So from graph, as AY increases, VY decreases. Okay, so what does that tell us? Well, since VY is decreasing, this means the quantity the 1/2 rho V squared bar is going to decrease. So as a result of that, this means the P bar must increase compared to what it was before. And since I said 2, we could really kind of get sneaky here and say the rho GH bar stays the same. So I actually didn't really like this language of 2 of the bars because you really only drew the H in the kinetic bar. So how you got points actually was this is how you got D1. You had to say that the kinetic bar decreases. And then to get D2, you had to say something equivalent to this relationship. As A increases, VY decreases. Now, if we're being really particular, you should have cited something about the graph, but if you just said this relationship, you get D2, where you have to say that there's an inverse relationship between the area of the pipe and the speed of the fluid. So this was a very tricky TBR. It was really hard to get a clean sweep, but I bet if we knew at least our basics with Bernoulli, we could get a good start with this. But I wanted to give a challenging fluids question because fluids is new, and that's usually the last thing people do, and there's not a lot of resources for it. So I wanted to show what a difficult fluids question could look like. So now we're on to easier things, though, even though it's still fluids. In experiment 1, students are asked to use a linear graph to determine the density of an unknown fluid. The students have access to a ruler and a wireless gauge pressure probe. Sometimes we just like to make up equipment. So we can have a ruler and we have a pressure probe. So I am going to tell you how to answer the lab question. So if you haven't really heard this before, the lab question, especially for P1, isn't really testing your physics. We use it to test your science skills. So most of this is about graphing and experimental design. The physics is worth maybe 3 or 4 of the 10 points. 6 of them are basically science points. So to start, it does not say write a procedure. It says indicate quantities that can be measured. So figure out what equipment they give you. They gave me a ruler. And they also gave me a pressure probe. So I'm measuring pressure and at some sort of a distance. Now also, to figure out what you need, it might help to kind of figure out how to relate these things. So ruler is distance, pressure is pressure from this probe, and we want the density. So a density equation with pressure in it and distance is pressure is equal to the reference pressure plus rho g times depth. But if we're looking at gauge pressure, the gauge pressure is just your pressure relative to atmospheric. So this means P gauge is just going to be equal to rho GH. So I often say if you're stuck, let the equation guide your experiments. Because especially in P1, you're not going to be asked to derive a crazy expression for any of these labs. So it is usually a formula sheet equation, or it's like one substitution or linking two things together. Like maybe you have a lab question that's this. Maybe you have to like set kinetic and potential energy equal, but it is not a derivation. You have to just look at the formula sheet and figure out how it relates. So, how do you do part A? You do not say, first I do this, then I do this. You say, what are the quantities I can measure? I don't even have to say how to measure it. I can measure the depth, which I'm going to call H, below the surface. And I can also measure the gauge pressure, P, in the fluid. Now, it actually doesn't have to be this gauge pressure. Like, absolute pressure actually works for this because that offset is sort of just an intercept. I did that purposefully. How do we reduce uncertainty? How do we always reduce uncertainty? We repeat for multiple values of H. Anything about repetition works here. That's the easiest. Don't overcomplicate it. Just say perform multiple trials for different H or P or average the results or anything like that. So how do you get A1 and A2? A1, you had to measure depth and pressure. I can't imagine anything else you would measure. Now, if you're a bit ambiguous with what the distance was, it's kind of a borderline case, but it's clear what you mean if you link it with the formula. So you can be generous with A1 and A2. It's probably not commonly missed. All right, so now what do we graph? Well, our formula says that P gauge is equal to rho GH. So what can we graph? Well, we found the gauge pressure at different heights or depths, H. No transforming was needed. This is linear. So I can graph the gauge pressure versus H. Now, it is very important, especially for the second part of B, that you say versus, not and. Because when we talk about slope, slope is rise over run, so it matters what axis is which there. Linear is linear, but please say versus. Like, we've had to give some people, like, we couldn't give them the point last year because they said they're talking about and, P gauge and H. So we couldn't figure out if their slope was correct. So we'll show kind of, this is my preferred method. And as a reader, your reader would thank you if you do an approach like this. So we had P equals rho GH. And we want to determine the density. So what we did is we said we are going to graph the pressure on the y-axis. And then we're going to graph H on the x-axis. And then in front, we have constants, rho and g. So here is like two really cool ways of just communicating this super clearly. Now, I like this way. This is a great way of doing it. Y-axis, x-axis, slope. This earns both B points in one line. Do not solve for the quantity. Like, I know that slope is rho g, so rho is the slope divided by g. I know that. You don't have to. We have to relate it. We don't have to solve. Another neat way, this is a less common one, but I like this. I've seen a couple kids do this, is we graphed the pressure on this axis. We graphed the depth on this axis. Then we got a best fit line, and the slope of that best fit line was equal to rho times g. Both of these actually earn both B points, if you're curious. So how do you get B1? You had to say a valid linear relationship. How do you get B2? You had to have a correct slope relationship. All right, I have no way of justifying this. I just needed to do some stuff with springs. I was a bit light there with the mass spring system. So in experiment 2, the students wish to calculate the force constant of one of several identical springs connected in parallel. Don't be scared of this. I know that parallel springs aren't in P1, but the equation is derived for you. So the students attach a block of mass M to 1, 2, 3, 4, 5, etc. springs, and we displace the springs, watch them bounce up and down, and determine that time of oscillation. So what is different from physics C is that in P1 and P2, sometimes we give you the equation, especially if it's something a bit out of scope. Because the point of this is not to test your deriving skills. We've done that enough. It is to test your graphical analysis. So you could actually derive this lovely expression that relates the period to the number of springs n. So it says the students correctly derive this relationship, and they plot t squared on the vertical axis. So we know, and it's actually going to be set up if we look. Spoiler over there. Oh, I didn't graph this. Oh, silly me. I guess we'll have to do a cut there. We see that t squared is actually put on the axis for us with units. So sometimes they force you into a specific linearization. So let's figure out what has to happen here. So label the horizontal axis, include units. We need to figure out how to make it linear. So t squared equals 4 pi squared times capital M divided by the spring constant K times 1 over n. So we already were told that t squared is going on the y-axis, and the variable here is n, because this mass M is a constant, 0.8 every time. And we're interested in solving for this K. So that means that our other variable is just going to be everything with n in it, which is 1 over n. So this is my x, and then as a result, my slope is 4 pi squared m over k. So to do that, I need a data table of t squared versus 1 over n. So I already pre-did this, where we plotted, I just did 1 over n. 1 over n is unitless, right? Because n is a number, so 1 over a number is still a number, and t squared is in seconds squared. And then we do my sort of running gag at this point, where anytime I do one of these lab FRQs, we always say, all right, going to take a quick break, going to do some mining off camera and do this best fit line, because you don't need to see me plot points, and I'm very error prone if I do this live. So we're about to see a cut because it is time to mine off camera. All right, what a successful mining trip that was. All right, here's our axes. So t squared was set up for us. 1 over n has no units. So here's how you get your C points. So the only really missable point here should be C1. So C1 is for your linearization, meaning did you pick something that's actually linear? And I did, because t squared was proportional to 1 over n. So that's why I graphed 1 over n. C2. Now, if you graph some variant of 1 over n with some constants in it, that's fine too. To get C2, this is your axes slash scale slash units. So just making a nice linear scale. Make sure to include a full scale, just so it's really clear. C3, this is the easiest point. You have to just plot the points in a reasonable way according to your data. And then C4 is the best fit line. So if you have a bad linearization, like you just know, oh, I can't figure it out, you can get C2, C3, C4. These are free points with this lab, as long as you commit to getting good units and have plotting the points properly and drawing a reasonable best fit line slash curve. So then we got to calculate K from this. I will always be a Desmos person because I suck at doing slope by hand. I'm bad at graphing. I'm bad at reading points. Rise over run, I'm sure I'm going to get the wrong answer because I'm bad at counting grid boxes. But you know what I'm not bad at? Plugging it into Desmos. You don't actually have to say this, that you use Desmos or anything. You can totally just spawn in the slope from nowhere. You get no points for the slope. You only get points for relating the slope to the thing you want. So if we go back up here, we said the slope of our best fit line was 4 pi squared m over k. So slope was equal to 4 pi squared m over k. So that actually earns us point D1. So to get D1, you have to say like slope equals blah, and it has to be correct. Now to get point D2, you actually need the correct number. So this is a numeric answer, so it's 4 times pi squared times m, which is 0.8. Or sorry, let's solve for k. So if we do this, we get k times slope would be equal to this thing. So all we have to do is sort of do some cross multiplying, and we'd get k is equal to 4 pi squared m divided by slope, which is 4 pi squared times 0.8 divided by the slope, which was 6.30. And if we work that out, we're going to get, oh, let's see, pi squared, that's about 9, then 0.8. I'm not going to pretend I didn't do this before. I don't know how I do this mentally, but typing it in, you're going to get pretty close to 5. And what are the units of spring constant? Well, force is k delta x. So force is in newtons, x is in meters. So the spring constant must be in newtons divided by meters to make everything work out. Don't stress too much about units. If all your graph units are right, there's a chance that we will not look at this. You did not hear that from me, though. We may or may not have actually graded units last year. I got to grade a question where we solved for friction coefficient, which has no units, and I probably saw every possible unit. But did they lose the points? No. Please get the units right, though. Don't assume this is a crutch. I think we argue that this point is hard enough to get itself that we don't want to make an extra barrier with the unit. But alas, that's the lab question. This is very routine. So when we talk about the lab being science skills, I needed to know nothing about pressure to know that I could measure distance and pressure from the sensor. I needed to know nothing about fluids to know that I could repeat for multiple values of H. So that's 2 points. Then I needed to know zero physics to tell me that this was the relationship that I could graph, because I gave you the formula. So if I saw that I could pull out the 1 over n, that gets me all 4 of the C points. So no physics needed there. So that can get you another 4 points. Now, if you didn't have the relationship and had to derive it, that may be 3. So realize you should be at like 6 points, maybe 5, without any physics application on this. So this is really a good time to point farm, is on this question. Now, you needed to know kind of some manipulating skills and regression to get this. D2 is one of the hardest points to get on the whole test. Usually this lab D2. All right. Now, our reward for getting this far is a QQT that I thought is at least decently accessible. I think the A part's a bit challenging, but B and C are quite straightforward. So here we have just a standard collision where a block is moving and it crashes into a stationary block. And we're considering the following different collisions. We're in scenario 1, the blocks stick together and move to the right. And in scenario 2, the blocks bounce off each other. So same incoming block, incoming velocity, but different results. It's a stick together or it's a bounce. And we want to compare the magnitude of the momentum change of the block with mass m in each collision. So we're asking, does the m block, which is the incoming one, does its momentum change more in the stick-together collision 1 or the bounce collision 2? So let's think about what that is. So again, remember, we're seeking physics facts here for our justifications. So we need to figure out what delta P is. So what is delta P? Well, momentum change is the change in your momentum, mv. So we're looking at the change in your velocity vector. So it might help to understand that velocity is a vector for this. So what this says is that delta P is proportional to change in velocity. Okay. Now let's actually go up here and try to figure out how that's going to relate. So we can say the block is moving to the right. So we're going to say it has some sort of momentum this way, P0. So in both of these scenarios, I know that my initial momentum is going to be the same value, P0. And I'm sure there's other ways of thinking about this, and you can run those by me as well. The QQTs always have the most interesting variations in responses. Now, in scenario 1, we know that I'm moving to the right, but if I'm picking up a bunch of extra mass that I'm dragging along with me, that must mean that my final momentum is going to be shorter, but in the same direction. So this means my delta P is sort of this vector here, right? Because I had to add a tiny bit of leftward momentum to get the right arrow to be less right. Now in scenario 2, I'm not sure how fast I'm going in the other direction. We can pick some random value. Now I'm sure if the speed was, like, it's pretty clear if the speed was something like this in the other direction, of course the momentum change would be bigger. So let's look at what happens if it's even a tiny speed the other way. So let's say it's a tiny speed the other way. So we'd get a momentum slightly to the left. So what's going to happen with that momentum change? Well, in the bounce, not only do you have to completely cancel your original momentum, so this would be if the block stopped, but you also need extra momentum to the left to build up to your final velocity. So actually, delta P is always going to be greater for a bounce because you have to fully stop the block and speed it up the other way. So it is true in general that the direction change changes your velocity more. So we can say for our second sort of fact statement here, we can say that reversing direction results in a greater change in velocity or momentum. Either way works. So here's how you get your points here. You get a point for saying that the bounce has a bigger change in momentum. And you get, so that's A1. Then you get A2 for relating your momentum to the change in velocity. And you get point A3 for somehow explaining that the bounce encapsulates the slowdown case, or like the fact that velocity is a vector and there's some sort of negative sign there. There's lots of ways to get this third point. If your explanation is convincing enough, if it's something that is in the spirit of this, kind of like we said last time with the TBR, like if it's in the spirit of this bullet point, you get A3. Also realize that the checkbox is like how I concluded. That's my conclusion, right? This is sort of me just stating what I know. Momentum change is going to be proportional to velocity change. So, and reversing direction causes a larger velocity change. All right, now we just got a straightforward derivation. Suppose in scenario 2, after the collision, the block of mass m moves with speed 1/3 v to the left. So originally we had this is what we had originally, was our block moving towards the stationary one, and that says after the collision, we're moving backwards at v/3, and we need to figure out what the speed is of the 3m. So this is, of course, conservation of momentum, right? Anything with just linear collisions like this is going to be momentum. So we just set up conservation of momentum. So P0 equals P final. So initially I have a block of mass m moving to the right and a block of mass 3m not moving. At the end, I have a block of mass m moving v/3 to the left. And then I have a block of mass 3m moving at a speed vf that I don't know. So now we can just solve, where we get mv would be equal to negative 1/3 mv plus 3 mvf. So I'd get 4/3 mv is equal to 3 mvf. So I can take out an m, and then I can divide by 3, and I get vf is just 4/9 of v. Quite straightforward there. So how do you get your derivation points here? Well, you get your first derivation point for saying that the momentum is constant, so any sort of statement of momentum conservation. You get B2 for correctly identifying the system momentum as mv. And then you get point B3 by working through kind of the details to get 4/9. And then a nice little conclusion here. Indicate which block, if any, experiences a greater average force exerted by the other block. Two blocks are colliding. Which is bigger, the block on m by 3m or the block on 3m by m? Well, that's just anytime you start getting into a tongue twister with different forces on, by, and it's just swapping their order. This is Newton's third law. This is just Newton's third law. Forces have equal magnitude by Newton's third law. This actually isn't the only solution, because you could have actually sometimes what we've done is we've actually talked about how you can come up with Newton's third law from momentum conservation. So there's another approach, kind of an outline there. If you didn't want to say Newton's third law, you could also say delta P is the same for each block, because for momentum to stay constant, any momentum lost by the m must have been picked up by the 3m and so on. So you could have also said, since delta P would be equal to F times delta T, and they're in contact for the same time, same momentum change, same contact time, F must also be equal on each block. So this is like an impulse momentum theorem derivation of Newton's third law. Now, I really intended for you just to say this. I tried to give you a gimme at the end, but we'll see. Yeah, so I thought this, again, my goal here with the free response isn't to make like the most reflective difficulty-wise, because that would be just a bit on the easy side. I wanted to try to give the content spread. So hopefully there were some things you got in here, and maybe a couple that made you think a bit. So I totally think that question 1, most of it was doable. A lot of points there that you could pick up. Question 2 is hard. The fluids question is hard, even though there's a lot of points to pick up. The lab question is always the lab question, not too much variation there. And then I thought there were a lot of nice things you could do on this QQT.